What I want to do today is talk about loads reconstruction, which actually is part of DesignLife today. And then we're going to talk about something we haven't done today at all about futures. And that is a facility we're going to put into DesignLife 11 to allow us to go in and select where gauges should go. Okay. So we're going to walk through a quick introduction, talk about what exists today, and we'll look at obtaining basically these strain histories that we need for analysis, where we can get those from. We'll look at measuring loads and structures, and then turn around and look at how that actually interacts with DesignLife in 9.0. And then at that point, we're going to actually go in and talk about futures and look a little bit about underneath the hood at what's actually happening with the loads reconstruction and how we can actually leverage some of the math there to go in and to provide the engineer a way to go in and select where to place the gauges to come up with a more precise transducer. Okay, and again, just stepping back and thinking about fatigue, we need to be able to go in and produce strain histories or stress histories to do fatigue on. And if we're looking at something like DesignLife, what we're doing is we're using FE stresses and measured loads of some sort, putting together to create these strain histories, but we need those histories one way or another. And so there's ways that we can go in and create these. And one is fully analytical, and you'll see some of this today looking at the auto companies where they can literally go in and have a digitized proving ground, run multi-body dynamics codes around a car around the track with specific tire models, recover all the loads in the structure, and use that downstream in fatigue analysis. And the key here is you need to be able to quantify that interaction for the loads. And so, you know, today we can go off and look at a tire model on a paved road, but it may not be appropriate going off and looking at maybe construction equipment digging into the ground or things where we can't really quantify the load interaction. But if we can, this is one approach for going off and doing that. At the opposite end of the spectrum, we could go in and just build a test model and fully instrument it, put strain gauges on it, and basically pull all the loads off that way. All the strains we need off that way. And again, what we'd be doing is using those strains for our fatigue calculations, which that means we need to go in and physically get the gauges in the right locations where we're going to have critical issues. What we're going to look at is a third approach, kind of a hybrid of the two. And what we're going to do is we're going to go in and we're going to use specific measurements to try to quantify the loads coming out of the structure. And then we'll use those loads downstream in DesignLife for fatigue. And there's two ways we could actually look at doing this. One, we could go in and look at taking traditional force transducers and introducing them into our structure. Or two, and what we're going to focus in on, going in and creating specific strain gauge measurements that we can turn whatever component we're interested in into its own force transducer. But once we have load measurements that we can pull out, we can bring those into DesignLife into our fatigue analysis, and again, use that to generate the strain histories downstream. Again, traditional force transducers have been designed to go in and allow us to basically go off and measure a specific load. It's basically a component where we've gone off and trying to isolate the measurements such that I can either extract out, you know, an axial force or a bending moment or a torque, but I've gone off and pre-designed this construction that will basically separate out and allow me to isolate a particular load or maybe a set of loads. To use these, we've got to go in and we've got to actually place these into our structure, meaning that I've either taken this additional piece of hardware and I've basically built it into my structure, and again, I'm kind of changing the load path, or maybe I've gone in and yanked out a part, replaced it with a custom-built part that is a load transducer for that. Either way, I'm changing stiffness, changing geometry. I'll probably have changed the load path. Now, some of these we're fairly familiar with. If you go out on the table, these are some HBM sensors that we actually sell. A lot of times in the road loads, you'll see that things like force transducers are used, between the wheel and the hub. But we're not going to look at this. We're going to look at basically an approach where we're going to take our own components and use strain gauge measurements to turn them into force transducers. And the way this works, I have a part up here, and I've got 2 loads on my part. And I've got 3 gauges. And as long as we stay within the linear regime, I can go in and look at the strains generated at a gauge from one loading and just sum that up with strains at the same gauge from a second loading. So I can use superposition to allow me to go in and to combine these. And if I visualize this, I apply my load 1, I will see a particular output from one of the strain gauges. And I can actually go off and quantify that in terms of the responses at each gauge from each of these loads. If I look at those equations at the bottom, I can go off and think about them another way. I could go off and just piece them together in terms of a matrix where I have my stresses are just basically due to the loads going in. And this matrix here, this is basically a sensitivity matrix. It's basically describing if I apply a particular load, each of these gauges do a particular output, the strain sensitivity matrix. And again, this isn't hard to do inside of DesignLife because we have this concept of virtual strain gauges. Virtual strain gauges allow DesignLife to go in and just lay particular gauges, T's, rosettes, single laid gauges onto an FE model. And again, most of the things that DesignLife does in terms of taking FE results and turning them into histories involve superposition. So it's going off, instead of looking at every node in the model to do superposition, do fatigue, we're going off and doing superposition to go in and to generate responses to the strain gauges. So what I have here are a series of virtual strain gauges I've laid on the model. This FE model has, in this case, the 2 load cases you saw earlier. And if I were to go in, run that through the virtual strain gauge glyph, and just dump the output to a display, what we get out of here now is basically for each separate load case I've brought in, I get a response of what the gauges are. This is that A matrix. This is that sensitivity matrix just basically being generated automatically by DesignLife. My challenge here was to use more equations than Andrew. So we'll go at this. What we have here is that matrix we saw earlier on, just taking the concept that I have a strain sensitivity matrix that basically relates loads to strains. And most cases, in order to do this, we need at least as many strain gauges as we have loads. And most times we have more. We have more strain gauges than we actually have loads. And that actually gives us a better result. And in that case, this response matrix can't be just inverted, to be solved directly. We have to go off and do a least squares fit. And what you're looking at here is basically going off and reordering the equation to solve for the loads using this least squares approximation. And one other thing to throw here, we'll see this in just a bit, is we're now actually calculating estimated loads, because there's some errors into the system that'll occur, and then we're doing a least squares fit through these. This is an estimated load prediction. But this is relatively straightforward to do. In fact, inside of the worked example 20, inside of DesignLife 9, we did this as just a worked example. It took everything that was existing inside DesignLife in terms of virtual strain gauge, and what we have down here is a scripting glyph, which is just standard part of DesignLife. And inside the scripting glyph, it's physically taking that math you saw in terms of going off and doing the least squares solution. And so I bring in strains, I bring in this response matrix from a virtual strain gauge. Inside the scripting glyph, it's going off and doing the math, and it can output these estimated loads. And that's just a standard part of DesignLife 9. And the idea here, it allows me to go in and to take a component and virtually turn it into a force transducer, and then bring in whatever I have in terms of measured strains and predict the output loads. Once I have these output loads, I can go in and apply them basically as inputs to my full finite model and do a fatigue calculation. This is all existing today. What we want to do now is talk about what we're going to do to take it to the next level, next release in version 11. And that is, in order to actually make this a good transducer, we have to get the strain gauges in the right positions. How many gauges we're going to have and where we put them. So in version 11, we're looking at going in and coming up with a way to allow us to instrument a component to actually give us, turn it into a useful transducer. And this is going to be a new engine inside of DesignLife. We're going to have a new engine. It'll have user control on how you specify where gauges can go. We'll basically go in and go through an algorithm to come up with the best placement to minimize the load errors. Again, give us the most precise measurements. And it'll actually give us a way to quantify how many gauges would be optimal to use. This is nothing that I've done. I've basically based this all off of work that Mary Wickham has done on her PhD. And actually the load reconstruction stuff was the same way. I think she's here today. So we're going to talk about taking this approach. And we're going to start back with equations we saw earlier. I kind of waved my hands when I said that we had these equations that basically related loads to strains. There was a parameter out here I had kind of ignored on the previous slide, and that is every time I have a strain gauge measurement, there's some error with that measurement. You know, the gauge has a certain sensitivity below which it can't measure the strains. There's calibration issues and placement issues, and so there's always errors involved with these strain measurements. And if I take and account for those errors, and so I go in and take the original equation I had to do the least squares fit, basically strains in through this least squares approximation to give me my estimated loads, and I put in now the quantities with the errors and do a fair amount of math. You can end up with an equation that basically relates the variance in the loads, basically the variance I want to see in my estimated loads, to two things. And one of these is this sigma squared, and what that actually is, that's the errors in the physical gauge measurements, you know, things like gauge sensitivity and calibration and things that are involved with me actually measuring the strains. We're going to kind of ignore those, saying that that's kind of outside my regime, that's to test people. But the second piece here is basically discomposed of the strain sensitivity matrix, and think of it, it's basically the multiplier that I want to move my strain measurement errors through to get load measurement errors. And what we want to do is try to control basically that quantity. If I can go in and basically control that quantity, I can generate the an estimate of my loads more precisely. How we're going to do this, one, I have to create that A matrix. So, you know, again, that A matrix is me placing gauges on the model, but now I have to figure out where I'm going to put the gauges. And actually, several things. How many gauges am I put on? Where do I place them? What direction do I point them in? And so in order to find that, we basically going to go in and go through an algorithm where we're going to first figure out on my part, where can I put a gauge? Because every place on a part I can't put gauges. You know, I either can't reach it, I have to put other things, you know, maybe clamps on this part, there's locations I just can't lay a gauge. Once I know where to put the gauges, I have to figure out what directions to put them in. And so we're basically go in and just put them in all directions and work from that. And then finally, once I have this basically identified locations where I could put gauges and all the directions I could put them in, what subset of those gives me the best response, this A matrix. So we actually have a working prototype of this built into DesignLife 10 using basically scripting glyph and just existing glyphs. And what it does is it goes through a process first where I present it with a model, and it goes off and finds all the free surfaces of the model, which is just a standard part of a DesignLife translation. So it's going off and finding all the free surfaces and identify all the nodes that are sitting on that free surface. Second thing it does is it allows the user to bring in a list of nodes that I can't put gauges on. And these right here are locations that the user has decided he doesn't want gauges. You know, we can't get gauges here because I actually have a clamp that's going to go onto that shaft. I can't have gauges inside the hole through here because I can't reach to gauge that location. But the user can control locations that he doesn't want gauges to be. That's very sexist of me. He or she doesn't want gauges to be. There's another test to go through. We can only lay gauges where we have like a smooth surface. And so there's a test that goes in once we know all the places where we can put gauges, and the user will allow us to put gauges. We look for things like sharp edges. And so there's a user-specified angle where we can go in and specify that if I see a break in the surface of a certain angle or more, I can't lay a gauge there because it's a hard corner. So those get weeded out of the possible locations as well automatically. And there is a test to go in and look at gauges that are sitting on surfaces that have small radii. You know, if I have a surface with a very small radii, I physically can't lay a gauge there. And so we'll find those and basically weed out those locations as well. When we get done with all this, what we end up with is a series of nodes that I can put the gauges. You know, the user will let me put the gauges there. It's basically smooth enough. It's got low enough curvature that I can go in and lay gauges. And so every one of these locations becomes a possible place to put gauges. And what we're going to do is go in and allow you to put gauges at a user-specified angle. So at every one of these locations, these nodes, the user will specify an angle that we want to go in and do. And virtually, think of it as a critical plane. I'm going to go off, and if I give it a 10-degree angle, I'm going to put 18 gauges at that location. So every one of those locations will be n number of possible gauges that we can run. Okay. And that's the starting point. With this information, we now have all the information that we would need to start selecting which gauges should I actually use in my transducer design. And to do this, we need to be able to go in and select the gauges. And what we're trying to do here is basically minimize the input, minimize that multiplier on the measurements from the strain gauges, the real strain gauges I'm using. In order to do that, and what we're going to do is we're going to go off and take that sensitivity matrix and actually take the sensitivity matrix transpose times its determinant. If I make that a determinant of that multiplied sensitivity matrix large enough, the larger I make it, the better my answer is going to be. So I want to maximize this determinant of basically A transposes to A. And this is basically called a D-optimal design. So we're going to go in and basically try to find a set of gauge locations that makes that determinant of that matrix the largest, and that's going to be our selection mathematically. So what we need to do is we've come up with a way to get all the locations that we could possibly run. We need to go in and figure out what set of those gauges give us the best determinant. And there's two approaches we could do. One, we could go in and just try them all. Just basically take a big hammer and try all the combinations. Or two, what we're doing here, we're using a numeric optimization. There's actually not built for us, actually. There's optimization routines that actually can take this information in terms of these various multiple sensitivities and find a combination to give us the best determinant of the matrix. If we do that, we have an optimal set of gauge locations to turn this into a transducer. Now, I had made mention that we also need to decide how many gauges we're going to put in. One, we have to have at least as many gauges as we have loads. So that's like the lowest, that's the minimum we have to deal with. There's a maximum number out there that may be determined by hardware. It's, I've only got 8 channels in my EDAC Lite, and so I'm limited to 8. Or as we add the gauges, obviously adding the expense, and so there may be an upper maximum that I choose as well. But what we're going to do is basically take the minimum number, take the user-specified maximum number and actually loop through this routine multiple times, generating selected gauges for each one of these different numbers of gauges. And we'll generate out of this, not only will we generate basically the selected set of gauges for this number of gauges, but we'll also go in, start to characterize what the benefit is by increasing number of gauges. Yep. Melissa's telling me I've got 5 minutes. I'm on my last slide. Perfect. Right now what we're looking at doing is going in and basically generating n number of solution sets, each solution set being an additional increase in the number of gauges. And there's several things we can look at here. But if we had seen that equation I had earlier on, we take the errors, put them to the least squares fit, and we come up with like a variance of these loads. I can go in and actually plot the variance of each of the load cases. And so what I have here is those variances plotted against the number of gauges. And what we're looking for here is either a physical value of the variance that I'm going to require for my transducer, or it may be that I'm going in and just looking at basically the I start to lose my benefit as I increase gauges, and so I can go here and see where I have diminishing returns and looking for like a knee in the curves where I see a big benefit going from 2 to 3 to 4, and beyond that all of a sudden the benefit dissipates. And what the user will be able to do is go off, basically look at these statistics and then decide which set of number of gauges he wants to use. Each of the numbers here will actually have a gauge file out there that we can go in and bring into DesignLife, as well as statistics, basically placing them, a location on the model, as well as orientation information. And again, what we're looking to do is allow us to go in and take just simple measurements, strain gauges on a part, and turn it into its own load force transducer. And the benefit here is that if I can use the actual part, I'm not basically altering the load path at all. One of the neat things about this is we're going off and doing basically linear algebra on these sensitivity matrix. I'm not trying to go in and to isolate individual loads to individual gauges. I'm going in and literally going in and relishing in the fact that if I apply this load, all these gauges light up, and I'm using basically linear algebra to kind of separate them out. We're really using the crosstalk between all the gauges rather than in a traditional transducer design trying to separate it out. And then as a benefit, again, if I go off and take this approach and I do have several discrete strain measurements on a component that I can use to calculate the actual loads, I can take those loads back into DesignLife, and now I have a full field stress history. I can look at the entire component in terms of fatigue. References and questions.